So as we've mentioned before, the main application for the quantum internet that we're going to be focusing on in this repository is the BB84 key exchange protocol. A key exchange protocol is a way to generate secret key, which you need, for example, to secure your credit card information as it makes its way between your home and the bank's servers. So you use your secret key to encrypt the information, and the bank uses the same key to decrypt it. But the thing is, as you use a secret key, you can't use it again. It gets used up and you have to make new key. And that's where key exchange protocols come in. All key exchange protocols that we use today are in principle breakable. They're very difficult to break, but they are breakable, meaning that as you make new key, not only you and the bank have the key, but a third party could also have the key. So as you generate new key and you send it to the bank, it's in principle possible for a third party to also get the key. But if you have a quantum internet, you can run the so-called BB84 key exchange protocol to perform key exchange in a perfectly secure way. I'm now going to explain roughly how the BB84 key exchange protocol works. I'm not going to explain why it works, just how it works. So our two communicating parties are Alice and Bob. And Alice and Bob would very much like to make a secret key that no one else has. So here's how they do it using the BB84 key exchange protocol. Alice starts with a random bit string. And she chooses another random bit string. And Bob also starts with a random bit string. Now Alice is going to encode each bit here in a qubit, and she's going to do that in a basis that depends on this bit here. So if the upper bit here is a 0, she's going to encode the qubit in the 0-1 basis. If the bit is 1, she's going to encode the qubit in the plus-minus basis. So here we have a 0 bit, and we know that the bit, because this is 1, we have to encode it in the plus-minus basis. So then she prepares a plus state, which is 0 in the plus-minus basis. And we keep doing the same for the rest of the string. So here's a 1, we encode it in the 0-1 basis, that becomes just a 1. Here's a 0, we encode it in the plus-minus basis, that's another plus. A 1, we encode it in the 0-1 basis, that's 1. 0 in the plus-minus basis. 0 in the plus-minus basis, 0 in the 0-1 basis, 1 in the plus-minus basis, and 1 in the 0-1 basis. And then she sends all these qubits to Bob. Now, depending on whether Bob has this bit, a 1 or a 0, he's going to measure in the plus-minus basis or the 0-1 basis. So if this is a 0, Bob is going to measure in the 0-1 basis. If it's a 1, Bob is going to measure in the plus-minus basis. So Bob perceives this state and sees that here he has a 1, so he measures in the plus-minus basis. And he correctly gets a 0. Now, another bit's coming in, and he measures in the 0-1 basis. So the bit's encoded in the 0-1 basis, he measures in the 0-1 basis, he gets a 1. Now a plus comes in, he measures in the plus-minus basis, correctly gets a 0. A 1 comes in, he measures in the plus-minus basis. This is the wrong basis, so the qubit's encoded in the 0-1 basis, and he's going to measure in the plus-minus basis. So what's going to happen is that he sometimes is going to get a 0, and sometimes he's going to get a 1. So with probability half he's going to get a 0, with probability half he's going to get a 1, which shouldn't happen. So let's mark this as an X, which stands for he measured in the wrong basis. Here he has a plus coming in, he measures in the 0-1 basis. Again, this is the wrong basis. A plus coming in, he measures in the plus-minus basis, that's the right basis, and he gets a 0. A 0 coming in, measures in the plus-minus basis, wrong basis. Minus measures in the plus-minus basis, and he gets a 1. 1 measures in the 0-1 basis, and he gets a 1. So now he doesn't know that he measured in the wrong basis here, because he doesn't know which basis Alice prepared her qubits in. So the next step is for Alice to send her basis string to Bob. so that he can compare. And Bob's going to do the same. He's going to send her his basis string. So they're going to compare these strings, and wherever the strings don't match, they're going to discard the qubits. So everywhere the strings matched, except where Bob measured in the wrong basis. So 1 1 0 0 1 1 0 1, that's the wrong basis, 1 0, and so on. So Bob now knows where he measured the wrong basis, and they both discard these bits. So they just throw these out. So what they end up with is the same string. So here, this is the remaining key string. So it's a 0 1 0 0 1 1. The reason this protocol is secure is that if an eavesdropper had listened in on this communication, this quantum communication, when Alice sent her qubits, these were going to be different. So Alice would have had 0 1 0 0 1 1, but Bob would have had some other jumbled string of bits. So 0 0 1 0 1 1, which is not the right string. So for Alice and Bob to know whether there was an eavesdropper or not, they're going to select a few of these bits at random, and they're going to check whether the bits match or not. So let's suppose there was an eavesdropper. So Alice has this and Bob got this. So they're going to select this, this, and this bits to determine if there's a mismatch. So here they see that the bits match, here they see that there is a mismatch. So they say, okay, there was an eavesdropper and we should now abort the protocol. That's what makes this protocol secure. So before you use this key to encrypt your credit card information, you know that the key is insecure and you abort the whole thing. Now, assuming that there was no eavesdropper, so Alice and Bob received the same string here. This is their secret key. That's how the BB84 key protocol works.